A geologist and a GIS expert walk into a bar, and the future of resource exploration changes forever. The contemporary search for economic deposits of minerals and hydrocarbons is now fully defined by the integration of traditional geological domain knowledge with advanced spatial computing. This collaborative relationship between the geologist and the Geographic Information System, GIS, specialist represents a fundamental paradigm shift. This synergy moves resource exploration far beyond old-school 2D map interpretation toward rigorous, data-driven, multi-dimensional analysis. This is not simply about digitizing old maps. It is about establishing a unified analytical framework that transforms huge volumes of disparate data into usable, actionable intelligence. A Geographic Information System, or GIS, is an integrated system of computer hardware and software designed to store, manage, analyze, and visualize geographic data. GIS is vital because it connects otherwise unrelated information by using location, defined by coordinates, elevation, and time, as the essential key index variable. Think of GIS as the ultimate digital filing cabinet and analysis lab for all things Earth-related. The geologist remains the foundational element in this partnership, developing the crucial exploration model. This model is the conceptual understanding of how a deposit forms, including its structural, lithological, and geochemical characteristics. The geologist provides the essential hypothesis for where and why resources might be found. In parallel, the GIS expert's technical role is to manage and harmonize the massive volume of geospatial data generated from satellite images, field samples, and seismic surveys. They ensure all this geoscience information, regardless of its format, shares a common, reliable coordinate system, a single source of truth. This seamless harmonization of data ensures integrity and reliability across the entire enterprise, eliminating the risks of mapping errors caused by siloed information. This digital transformation liberates the geologist from the laborious task of manual data integration and map overlay. The geologist's role is elevated. Instead of spending time on manual data handling, their intellectual capital is focused on strategic model definition, validating the sophisticated outputs, and refining the conceptual geological understanding. They shift from being a data mechanic to a model architect. Because, let's be honest, no geologist wants to spend all weekend trying to align a geochemical map from 1985 with a modern seismic section. One of the most powerful results of the GIS geologist collaboration is quantitative mineral potential mapping, or QMPM. This process moves exploration beyond subjective assessments to statistically rigorous prediction, ensuring that costly drilling campaigns are focused on areas of highest probability. Case studies confirm the power of this approach, demonstrating that advanced GIS methods can increase discovery rates by 30 to 40%. A cornerstone technique used in QMPM is the weights of evidence, or WOFE method. WOFE is a mathematical tool for combining multiple map layers, known as evidential themes, to estimate the favorability of a location for a specific deposit type. The model calculates statistical weights based on the measured spatial overlap between known mineral occurrences or training points and geological features like proximity to fault lines or specific rock types. A positive weight suggests that mineralization is statistically associated with that feature, while a negative weight means that feature is statistically unfavorable. This quantitative feedback loop is essential because it validates or challenges the geologist's initial hypothesis, often revealing spatial relationships that were initially unexpected. This forces the geologist to refine their understanding of the true geological controls on mineralization. However, the WAFI method operates with a critical statistical assumption called conditional independence. This means it assumes that the predictive influence of one layer is independent of another. In complex geological environments, this assumption is frequently violated as geological processes often lead to mutually interrelated predictive patterns. When this condition is violated, the model introduces bias and tends to overestimate the largest posterior probabilities. In plain language, the most favorable areas appear even more favorable than they truly are, which could lead to financially devastating drilling campaigns based on a biased spatial prediction. To counter this bias and ensure model reliability, advanced statistical methods like weighted logistic regression are often utilized as they remove the constraint of conditional independence. This need for statistical rigor confirms that the modern geospatial analyst is evolving into a specialized data scientist. The mining industry has seen profound changes through this partnership, particularly for gold exploration. The ability to integrate satellite imagery, topographic maps, geological surveys, and geochemical data provides a unified platform for efficient target generation. The Nevada Goldfields case study showed the immense benefit of integrating real-time drone imagery, hyperspectral analysis, and historical drilling data within an advanced GIS system. This system allowed geologists to recognize subtle mineralization patterns and structural signatures that led to a significant 30% increase in drilling hit rates, drastically reducing exploration costs and streamlining site selection. In the Witwatersrand Basin in South Africa, a globally productive but geologically complex area, state-of-the-art GIS platforms integrated extensive historical mining archives with modern seismic data. By constructing detailed 3D models of subsurface structures, the project achieved up to a 38% improvement in spatial accuracy for ore body modeling. This dramatic improvement optimized resource recovery and enhanced safety by precisely mapping fault lines and potential water ingress zones. Meanwhile, in the Pilbara region of Australia, where challenging overburden conceals gold deposits, exploration successfully combined GIS with machine learning for predictive analysis. This predictive modeling drove a 35% increase in exploration accuracy, leading to new discoveries in areas previously deemed low potential. Turning to the hydrocarbon sector, oil and gas involves monumental financial risk and technical complexity, making GIS integration an indispensable component of the workflow. Traditional 2D geological maps provided insufficient resolution for identifying deep trapping mechanisms. 3D GIS technology has revolutionized oil exploration by providing the capacity to visualize and analyze the subsurface structure in 3 dimensions. This is essential for ensuring a comprehensive understanding of potential risks and opportunities associated with drilling operations. This visualization capacity allows geologists and geophysicists to effectively overlay critical data types, seismic readings, well logs, and satellite imagery onto a single platform. This combined view is crucial for identifying geological features such as stratigraphic traps, structural highs, and fault systems that are indicative of oil and gas deposits. Furthermore, GIS facilitates the crucial process of reservoir characterization, allowing geostatistical methods to be applied to seismic and sonic logs to predict trends in stratigraphic traps and evaluate porosity within formations. The effective management of this geophysical data is the primary step in condensing underground reservoirs into viable prospects. In Romania's Izvor oil field, integration proved necessary for holistic exploitation planning. The team needed to map, analyze, and present all factors involved in resource exploitation simultaneously by overlaying the technical 3D seismic reservoir model with critical surface components, including social infrastructure like roads and houses, and environmental constraints. This comprehensive spatial view ensured that drilling proposals were both geologically favorable and operationally feasible, supporting multidisciplinary decision-making. The advanced 3D systems also facilitate drilling optimization. They allow teams to model various scenarios and simulate drilling paths, which dramatically reduces financial risk and minimizes the environmental footprint associated with exploration. In a definitive case study in Alaska's Mid-Elbert Prospect, 3D seismic interpretation and modeling successfully predicted and located thick methane gas hydrate intervals, confirming the high precision afforded by this technology. GIS plays an equally vital role in asset management after exploration, particularly in managing extensive pipeline networks. The oil and gas industry traditionally relied on methods that could not produce the survey maps needed for real-time applications, leading to major drawbacks in terms of planning and responding to natural disasters, equipment failures, or human error. GIS technology addresses this by generating digital maps that show oil and gas pipelines as well as other relevant features such as terrain, vegetation, and settlements. This spatial data is linked to a relational database containing pipe attributes like diameter, date of installation, pressure, and soil type. This allows operators to quickly query the database for essential information such as the next required maintenance date, or to instantly identify areas prone to sabotage or previous spillages. The integration of GIS with supervisory control and data acquisition, SCADA systems, and satellite monitoring enhances real-time oversight and predictive maintenance. This proactive, four-dimensional space and time system is crucial because safety and environmental risks must be monitored continuously. After all, the only thing worse than a dry hole is a pipeline leak on a busy road because your maps were drawn in pencil 50 years ago. The powerful capabilities of GIS rely on cutting-edge data acquisition. Geospatial data for exploration is captured using various remote sensing methods, including aerial surveys, drones, and high-resolution satellites. Satellite mining imagery in particular has become a game changer, helping to reduce exploration costs by up to 15 to 20% by pre-screening large land masses. Remote sensing technologies include optical and multispectral imagery, which offer detailed views of the terrain and provide rich data on land surface composition and vegetation health. Hyperspectral imagery is an even greater advancement, capable of analyzing hundreds of narrow spectral bands. This allows geologists to distinguish materials with incredible precision, using spectral matching algorithms to identify exact mineral types and their concentrations. For critical infrastructure monitoring, synthetic aperture radar, or SAR, is invaluable because it can penetrate clouds and capture data at night, making it reliable in all weather conditions. SAR is essential for detecting millimeter-level ground movement using INSAR technology, which is critical for assessing the stability of slopes, tailings, dams, and overall site security against hazards like landslides. These remote sensing tools, combined with GIS, form the bedrock of the industry's digital transformation, boosting efficiency, ensuring safety, and improving operational reliability across the board. The convergence of GIS with artificial intelligence, AI, and machine learning, ML, brings in a new era of possibilities, often called Geo-AI. AI accelerates the extraction of insights from complex data, automates feature extraction from massive datasets, and improves predictive targeting. When AI is combined with GIS, it allows for real-time monitoring and predictive analytics, enabling companies to proactively control and prevent spills or anticipate equipment failures before they occur. Furthermore, cloud computing enables collaboration between decentralized teams, allowing real-time mapping data to be securely shared globally for fast, data-driven decision-making, accelerating exploration outcomes. the integration of the geologist's domain expertise and the GIS specialist's technical precision is fundamentally reshaping how we discover, exploit, and manage Earth's resources. This collaboration establishes a holistic spatial science that reduces financial risk, shortens discovery timelines, and ensures a lower environmental footprint compared to traditional, less targeted methods. As we look ahead, the modern geologist must embrace AI, cloud systems, and real-time georeferencing to remain at the forefront of discovery. This shift is not just about adopting new tools. It is about fundamentally rethinking the process of exploration to make it smarter, faster, and more responsible. If you are interested in these subjects, please subscribe, hit the like button, leave a comment, and share this channel with your friends. Until next time, keep exploring.